Hi, student, back to Smith chart again. Last time I'll talk about how to use the Smith chart to find input impedance of the whole system when you have the load impedance ZL connected to the transmission line that have characteristic impedance Z0. What you need to do is you need to find the length of the transmission line in the term of lambda, and then you find ZL normalized, which is equal to ZL over Z0, correct? And then you plot ZL on the Smith chart when your ZL normalized has the real part or resistance plus JX, that's the imaginary part or reactance, and then you see the circle here, 0.1 circle, 0.2 circle, that's represent resistance R or the real part. And start from the left, you're going to have your R to be 0. You can see this is the small number and start increasing when you move to the right. And at the right end of the circle, you're going to have your Z to be your infinity. And for these lines represent imaginary part of your impedance or reactance. So at this point, when you know your ZL connected to the transmission line, and if you want to find the input impedance of the whole system, what you need to do is you need to rotate this point when you take the center of the Smith chart to be a reference point for rotation. And the direction of rotation, you take a look at this one on the Smith chart here, wavelength toward generator. So the same thing, it's just you start from your load impedance and you want to move to the left into the source, or this we call generator. So the direction of rotation is going to be clockwise, okay? And how many degrees that you want to rotate here is depend on the length of the line in terms of lambda. So you take the reference point here as ZL normalized, and then you just rotate in the direction of clockwise for depend how many lambdas of your transmission line, or the length in the term of lambda. And when you find the final point here, you can read the real part and the imaginary part here, that you can find the input impedance normalized. Okay, and the same thing if you already know the input impedance of the whole system, and they want you to find your load sorry, impedance. What you need to do, you need to move from the left to the right into the load, and that's result in the direction of rotation is going to be opposite direction, or in terms of counterclockwise, just right here, wavelength toward load here. And for example, if you have your input impedance at this point here, you need to rotate in the direction of counterclockwise, and then you find the final point, and you read it out to be your ZL equal to R plus J omega X. That's what we left behind from last YouTube or Smith chart series 2. Now for this lecture here, what I'm going to talk is about the transmission line meshing. You take a look back at your transmission line system again. When you have your load impedance connected to the transmission line, and the transmission line here have the characteristic impedance to be 0. I will pick up my lecture note. Sorry, that's in time, but I will explain in English. So let's start with the system that has the characteristic impedance to be R0 here, and your load impedance is 25 minus 50 J ohms, and you know exactly that your ZL is not equal to RL. In this term, you know that your transmission line is not matched. That means your ZL is not equal to Z0. Okay, because you're going to have your reflection coefficient here to be your ZL what minus Z0, right? And then divided by what? ZL plus Z0, right? And what we want, just like I explained to you, that to have the transmission line match, that means your ZL has to be equal to Z0, and you end up with your deflection coefficient at the load to be 0. But for the case, somehow, or in case you cannot change your ZL to be equal to Z0, what you need to do, you need to bring another transmission line connect in parallel with the original transmission line here, and the new transmission line here we call it as Stub, STUB, which can be either open circuit stub or a short circuit stub. And what you need to find out is you need to find the position that you're gonna bring your new stub into the original transmission line. So I put the position from the load, move to the left to be L1, and also the length of your stub you need to find out, as well. I put this one as the length to be L2. You're probably wondering, how the system work. It's a little bit complicated, but if you follow my lecture, hopefully I will make you more understand about what's going on, in the system here. Okay. Well, before we get into the steps to make the transmission line match, I'll show you a bit about what we need to do some change to the system, because you're going to bring the new transmission line connected to the original transmission line here, and your system is not so it's inconvenient for you to work on the impedance, because you put let's say impedance in parallel, because you know that your total impedance of the whole system, when you have impedance in parallel, your total impedance going to be equal to 1 over Z total. It's have to be equal to Z1 plus 1 over Z2, correct? So it's better to work on something that we call admittance. YT simply equal to Y1 plus Y2, because you just add them up together. So the first step we're going to do is we're going to convert the impedance system to be your admittance system, and of course we're going to use the Smith chart for this job. So let's see how the system works. Okay, I'll start over again. Now we're going to talk about the admittance system here. you have your ZL connected to the transmission line with the characteristic impedance Z0. And now what I'm going to talk about the admittance system. So I'm going to talk about YL normalized here, and you have a Y0 here. And what is your Y0 normalized? Y0 normalized, simply you divide Y0 by V0 and just give you 1. It's pretty much the same as the impedance, because you know why your ZL normalized simply equal to what? ZL divided by Z0, correct? And if you want to work on the admittance system, when your ZL equal to 1 over YL, so your YL simply equal to what? 1 over ZL normalized. So this give you Z0 over ZL. So when you want to find your admittance normalized, you multiply Z0 by 1 over ZL. And what is your 1 over ZL? 1 over ZL equal to YL, correct? So when you want to find the load normalized, load admittance normalized, you simply multiply Z0 by your load impedance. So it's different than when you want to find the load impedance normalized, you simply divide your ZL by Z0. Okay, and then this is how it works. Let's start again before we are going through all the steps of the matching transmission line. Now you have your system to be YL normalized, and this is your characteristic impedance, admittance normalized is become 1. YL normalized is not equal to Y0 normalized. For example here, you have YL to be normalized to be 0.4 plus 0.8 J. I will go through how to get this number again, okay, by using Smith chart. So basically when you have what are you going to do? I just give you the rough idea here, okay? This is the Smith chart. If you plot your ZL normalized on the Smith chart, you want to convert your ZL normalized to be your YL normalized. So what you need to do, because 1 over YL normalized is simply equal to let's say let's put it this way, your load admittance normalized simply equal to 1 over load normalized load impedance. So actually you're going to have the different phase to be 180 degree or 180 degree out of phase. So what you need to do, you need to take the reference point here, the center of the Smith chart, and then you draw a line and you find YL is going to be at this point. It's 100 degree out of phase, okay? And when you have YL normalized, from the problem is give you 0.4 plus 0.8 J. Okay. The position of YL here on the plot is going to be different than this, but I just give you the idea how to get YL when you have ZL normalized here. So if you take a look at this one here, the next step is that since you want to match the transmission line and you cannot change your YL to be equal to Y0, so you need to bring a new transmission line connect to the original transmission line here and make the whole system here. When you look at this one, it's going to give you a new YL. Okay, I put it this way to be what? Can you tell yourself, what if you match the transmission line, what YL normalized, the new one should be what? It should be equal to the characteristic impedance. Sorry, it should be equal to characteristic admittance of the transmission line. So what you're looking for is that you want this one to be 1. It's like you bring the newer load admittance, connect to the transmission line here, the original one, and you want is equal. That's mean 1. But you look at this one here. When you start with YL normalized, you don't have YL normalized here equal to 1, right? But what you're looking for is that you want is equal to normalized admittance, which is 1. So you need to change this one here, the real part. This is already the real part. You want this one to be 1, and you want to get rid of the imaginary part or the reactance. So that's what I'm going to explain to you. How to get the final number of Y final to be 1. Okay. So let's take a look at this again. When you look at the Smith chart here, because you have your YL to be at this point here, and you take a look at the transmission line here. This is your YL normalized, and you take the reference point here. Okay, this is your lambda of YL normalized. That means you have the reference point at YL normalized to be your whatever lambda you have here. And then you also have since you want your whole system here, when you have the new transmission line connect to the system, you want it then up to be your Y at this point to be your equal to normalized characteristic admittance, which is equal to 1, correct? So you need to first you need to get the real part to be 1. How do you do that? So the first step is that's why I mentioned you are looking for the position L1 that you're going to bring a new transmission line or stub connect to the transmission line here. When you bring the new transmission line connect to the system, if you take a look at only your, let me put it there, if you look at only the position of your transmission line here with YL connected to the end of the line, You want this end up to be y l new. I put prime here to be 1 plus j something. Let's put a here. And you know that you already got have the real part to be 1. And the next step to wrap it up to get the new or normalized admittance to be 1 to make the transmission line match. You simply get rid of the imaginary part here, J, by using the stub with the proper length. Put as L2, and you will see that the stub that's connected to the transmission line here is give you only the imaginary part. So you're not doing nothing with the real part. The real part still be 1. And when you add them up, because you're talking about an admittance system, you simply add them up together, and the imaginary part, this one, going to be cancelled out by the normalized stub admittance with the proper length L2. You cancel around, and finally you get the normalized admittance to be 1, and you make the transmission line match. Okay, let's give you the rough idea. You probably not see your clear picture yet, but let's work together on Smith chart here. Okay, I'm going to go through my lecture that I already have my switch chart here. Let's blow it up. Make it 150. All right. Well, we start with the whole system with the Z0 equal to what? 50 ohms, and your ZL equal to 25 minus 50 J ohms, and you have a ZL normalized to be 0.5 minus J. Okay, where is your 0.5 minus J? This is your normalized load impedance. So I'll start with here. ZL equal to 0.5 minus J, because this is my 0.5 circle here. So I move around, and you need to find negative J. As I told you before, the upper part of the Smith chart here is give you a positive number of imaginary part, and the lower part of your Smith chart here is give you the negative value of your imaginary part. So where's my negative 1? This is my 1.0. So I have the intercept point at this point, and this give you ZL normalized. And since I mentioned earlier about what we need to work on admittance system, so I'm going to convert my normalized load impedance to be normalized load admittance. So I simply go through the opposite sign when you have the center of your Smith chart as the reference point. Or let's make this point and find a new one, where the new point is going to be 100 degree out of phase of this point. And then you have this one, step number 2. You have YL equal to 0.4 plus J 0.8. This is 180 degree out of phase. Okay. And if I show you here, I'll change this one to be YL normalized, and I have my reference point here, because this is, you draw a line, pass through YL normalized. You have the reference point to be lambda YL, and I have it right here. Now, as I told you before, to make the transmission line match, you want your this part of your transmission line, when you add them up with the normalized admittance of the stub, you want this one end up to be Y normalized to be 1, because this is Y0 normalized also 1, so they all are equal, and then the transmission line is match. Okay. So what you need to do, you need to move your normalized load admittance to the left toward the source, or toward generator. Sorry. This means you rotate that point in the direction of clockwise. That's why I have here, I'll start with normalized load admittance. I rotate here for until you intercept the circle of 1.0, because you want the real part to be 1, and you read the point here, the real part, of course, that's what we're looking for, is 1, and you end up with the new value of the imaginary part. Now change from 0.8 change to be 1.6, and you find the reference point of your Y in, or just the portion of this part with the load admittance connected to the original transmission line. Okay, it's not really dealing with the stub at this moment. So this just give you the position, the difference between 0.179 and 0.115 lambda. You subtract 0.179 lambda from 0.115 lambda, and then this give you 0.064 lambda. That means this is the position that you're going to bring the stub connect to the original transmission line. Okay. Or simply is make the real part of your normalized load admittance to be 1. Okay, the next step is that you want to get rid of 1.6. So you know exactly that you are looking for the normalized stub admittance to be what? Negative 1.6J, correct? And you have option, either short circuit stub or open circuit stub. Let's start with the short circuit stub. Okay, now you take a look at the short circuited stub. Look like this. So what is your, let's start with the ZL. We're talking about a short circuit. Your ZL equal to what? The ZL equal to 0, correct? It's both the real part and imaginary part becomes 0. This is R, sorry, and this is X. They both equal to 0, 0. So where's the position on Smith chart? Let's give you R equal to 0 and X equal to 0. You start at this point, right? Because R, like on the circle, you start from 0 and the number increasing when you move from the left to the right. This one is 0 0.1, 0 0.2, and of course this one is infinity. And you take a look at this one here. For imaginary part, this is 0 0.1, this is 0 0.2 of the imaginary part. So this part also gives you imaginary part to be 0. And since we work on admittance system, you need to find the admittance system, the admittance, or YL normalized, which is 100 degree out of phase of their impedance. So you have the position start from here, and since you want to find you want to get rid of 1.6 J, you're looking for the stub with the proper length that give you normalized admittance to be negative 1.6. So raise your negative 1.6. You need to work on the lower part of your Smith chart because give you the imaginary part value to be negative. So this is my 1.6. And if you notice when you're talking about a stub short or open, even you're talking about your Z or Y normalized has the real part and imaginary part. You can see when you have short or open, you never change the real part. The real part still becomes 0, right? Because you just move around at the outer part of your circle here. You never change your real part. You can change only your imaginary part. And this is what are you looking for? You're looking for negative 1.6 J. And that will give you the proper length of the Smith chart to make the transmission line match. And this gives you L2. The reason that you need to pick up, you need to start from the short circuit, start from impedance to be 0, and then you work on admittance system, so you find your admittance at this point. That gives you the starting point of your transmission line or the stub. As you move from the right to the left, so you move forward to generator or to the source, you need to rotate this point in the direction of clockwise until you hit negative 1.6 J, and this gives you the length of your stub. Since this one is 0.25 and this one is 0.339, you can find the length. Simply subtract becomes 0.339 lambda minus 0.25 lambda and give you 0.089 lambda. So if we draw the whole system here again, you get a solution. First, you have your ZL and you have Z0. And this one gives you the position of on the transmission line, original transmission line, that you will bring the stub connect to it. So it becomes 0.089 0.064 lambda. This is your D1. Okay. Because this is the reference point, I just point you out. This is your load admittance, and this is the position that you will bring the stub connect to the transmission line here. And you have the stub with the length L2 as we calculate from down here, becomes 0.089 lambda. Okay. So you look back again when you have your ZL not equal to Z0, the transmission line is not matched. What you need to do, you need to help of the stub that connect to the transmission line and make the whole system have, this is the whole system, have your ZL finally normalized equal to Z0, and you make transmission line match when you cannot change your ZL, so you need the help of the stub. Okay, you look back again what I explained, and then you probably understand more. There's still much more to explain, about the whole system here, but just to make sure that you are clearly understand about what's going on, when you want to match the transmission line here. So let's say you want to match again. What you need to do, since this is the system is in parallel, so it's better to convert the system here to be your admittance system. And from ZL normalized, you know how to find a YL normalized. And then you need to find the position that you will bring the new stub connect to the transmission line. And I put the position from the load to the left to be D1. This is the position here. You're concerned about only the portion of the transmission line here with your load impedance connect to it. You're looking for something, you want Y in here to be 1 plus something. Okay, because if you want to the transmission line match, you know exactly that the normalized admittance of the whole system here has to be equal to the normalized characteristic admittance of the transmission line, which is equal to 1. So we need to make the real part here to be 1 first by take some portion of the original transmission line, and you end up with the Y in equal to 1 plus J 1.6, and you still have J 1.6 here. So you need the help of the stub that connect in parallel to the transmission line here, and that's why you need to find the proper length of the stub, or the short circuit stub here. You need it to be negative J 1.6, and I already explained how to find the length of the stub to give you the normalized admittance to be negative J 1.6. Okay, and actually this there are more than there's more than one actually, the position. If you take a look at this one, since I explained that the position that you want to bring the new stub to connect the transmission line in parallel, let's say is L1, you want the portion of the transmission line and the load connected to it to be Y in equal to whatever that has the real part to be 1, just like this. So you simply rotate the point of normalized load impedance in the direction of clockwise until you intercept the circle r equal to 1.0. And you can see that it's obviously that you can intercept at this point. This is your circle 1.0. But if you move more, this also intercept 1.0 circle. This still are okay. You can also use this point. So that's mean when you start from YL normalized here, you end up with the other position here, and that's mean that your length of the line have to be the position from the load to the left here has to be further from the load. Okay, and if you rotate again, it's come back to the same place. It's just like become even further. Okay, so that's give you ideas. You're not really limit to only the point number 3. Now what about the open circuit stub? Well, everything you do the same thing. You have the load connected to your transmission line here, and then the position that you will bring the stub connected in parallel to the transmission line is still the same here, because you have the real part to be 1, right? But for your open circuit, what the open circuit stubs are here? For the open circuit stub, what the difference is that you have to start from your ZL to be what? Open circuit infinity, right? Where's your infinity? So at this point. And when you want to work on the admittance system, you have to find a new point that's have 180 degree out of phase of this ZL normalized here, so it show up to be at this point. This is start from here, and then whenever you want to cancel route of your imaginary part of your Y in, for example, here you need like negative 1.6, whereas your negative 1.6 is right here, but your stub, the open stub, you start from this point. So what you need to do, you need to rotate here in the direction of clockwise. So you're going to have end up with a very long stub. So in practical, we're not going to do that. So that's why they prefer the short circuit stub. Okay, so that's all about our steps, how to match your transmission line